but the day went by fast, and that's not normal. And I'm excited about feeling this way in the future and making these videos. Thank you for watching and clicking on this video, by the way. I'm really, really interested in, like, if you don't know what this is, first of all, this is tennessine, the new element, 117 protons, atomic number 117. They just named it, like, what, a couple years ago? No, November. Okay, so, God, before Trump was president is when they named tennessine, the element tennessine. I live in Tennessee, so this is cool, or it was cool, or whatever. But so this is a new element that we synthesized. Like, have you ever heard of this? So it's what they do is basically they put they take some atoms, some elements like, calcium and something else that's heavier. I think this one was specifically calcium and something. Anyway, they take two elements whose atomic numbers, when put together, add up to another number that they're trying to synthesize. And they take, they have one atom sitting in place, and they shoot a beam, or not, well, a beam, a stream. They shoot a stream of the other, uh, the other kind of atom at the first one so fast that it can avoid the magnetic repulsion of atoms. All atoms repulse each other. That's why when you touch something, you're really not touching it. You're not putting your finger through the electron shells of someone else's hand if you touch their hand, obviously. But so the protons and neutrons in the middle of those two atoms actually combine for, a couple attoseconds or whatever. And, like, if we can prove that that happened and existed for a certain amount of time, then a new element existed. And we did that. And that is so fucking cool to me that we can, like, synthesize elements. And actually, they theorized this for a while, but thought it was impossible because of how unstable elements get the more, the heavier they are. Like anything after, is it plutonium or uranium, is has like a half-life of, like, a day or something, right? I think I read that on this page. I read this page the other day. That's why I'm talking about this. I read this whole page, not the whole page. I read like a majority of this. And I'm not saying that I'm smart enough to understand all of it and all the jargon, but, like, took AP Bio and, like, AP Chemistry, and not AP Chemistry. I took Chemistry and AP Bio, like, in high school. Actually, well, I mean, I took a little bit of bio in college, but I understood enough of this to know how fucking cool it was until, like, understand it at, like, 4 a.m. or whatever. And if you can read it here, Island of Stability. Okay, so, like, there's something about the the reason they're so unstable, heavy they are, is, like, the protons have this, like, repulsion to each other as well, like, inside the shell, you know? So, like, the more protons are in the shell, the more they don't want to stick to each other anymore, so they decay. So they, like, and the same thing happens with these super heavy elements, but I'll get to that in a second. Like, so the reason that how do they put it? Okay, so they're unstable because they don't have stable isotopes, which means that they don't actually exist as that element for very long. Like, if you had some, 20 pounds of, like, element 101 or something, well, it literally would not be that element after a couple hours. It would decay protons and radiation. Like, it would shoot hydrogen electrons and shit at people and, radiate, and then it would, like, I don't know, blow up or some shit. I'm not sure how 20 pounds of a half-life decaying shit. I don't know how that actually happens in the real world, but the atoms change. They decay. They lose protons and neutrons and electrons and shit, and it becomes different elements. It's not that element anymore. It doesn't exist as that element anymore. So when that doesn't happen, like with fucking iron or something, it's called a stable isotope. And there's so many protons and neutrons and electrons in higher elements in the like hundreds, that we thought that anything heavier would just not even exist for like a nanosecond. But they have this theory that if you know anything about electron shells, I know this is high level shit, but it's just so cool to me. This is probably all I'm going to talk about for the rest of the video, so if you don't want to watch it, that's fine. But okay, bismuth. I actually haven't read this in a couple days. So it says that, you know, so the island of stability, from what I understood reading this, is that at a certain point, there's another electron shell that gets completed when you get to a certain weight, and that makes it so a lot more stable than we would think for based on its atomic number. Like, so this here, for how many protons are in an atom, which is what its atomic number is based off of, and that's why adding protons together makes a new element. Because literally changing the number of protons in an atom literally changes what element it is, what substance it is, which is crazy to me. When they told me that in school, I was like, are you kidding me? We can just add protons, it just becomes something else. So yeah, it's like, you know, this 20 pounds of shit all has 20 protons. It must be whatever atomic number 20 is. If you add one to each of them, it's fucking the next one, you know. But they also have an equal, each atom has the same number of protons and electrons. Electrons spin around the atom at like near light speed, and the protons stay in the middle, not moving very much. And, well, you can't just have 40 electrons, you know, all spinning around in one circle around an atom. You ever seen a picture of an atom? It's got like, you know, 6 little circles in the middle and then like 3 rings spinning or whatever. Well, those 3 rings are because, first of all, the electrons have to be theoretically like equally spaced to like never hit each other, because if they do, it throws off the magnetism if they get any closer than they're supposed to or some shit. Well, the first ring around the proton group is just 2 electrons. And then the next one is a little farther out, and it's got 8 that are equally spaced. Well, it only has space for 8, which doesn't make sense to me exactly, but they say that each ring has a certain amount of space. So the first ring can only hold 2, and then apparently if an atom has 3 protons, then it has 2 electrons on the first ring and just 1 on the outer area. Isn't that crazy? But then it moves up to 8, and then 18, and then 2 shells that are 32 electrons, filled with 32 electrons, apparently. And then the next one has 18, I guess. I'm not sure if that's always how it works, if it fills up, you know, like if you have like 29 electrons. Not 29. If you have enough to fill up the first 3 shells here and then another 32, does it automatically... There was something about that I remember in class. It was like it doesn't fill up the 4th shell before it goes to the 5th shell or something. Something about that. Anyway, that was the part that I never really understood, but what I'm trying to get to is that the reason that some elements are kind of unstable and very reactive when they do chemical when they react with other elements, they're very like explosive. That's because elements apparently don't like the state of not having a full electron shell. Like if they had 2 in the first one and 7 in the second one, they would really want 1 electron from another atom. Or if they had, yeah. So it makes them really easily it makes it really easy for them to bond with other elements and atoms and stuff. Like they'll grab on to another electron in like let's say that, you know, they have 2 and 7 in this one, and something else has 2 and 9. You know, they have 2, 8, and 1. So the 1 from that one and the 7 from this one will link, and it'll make like a singular bond, and that'll become a new, you know, molecule, which is crazy to me. But that's actually how it works. They literally, that one electron like connects them, like that they become connected by that electron. Just again crazy in my opinion, but like, you know, does it just stay there and the other ones just spin? See, I don't know. Anyway, um, but there's something about how uh, having a full shell makes it more stable, and once you get past a certain atomic number, that new shell is completed, and then like, you know, all those electrons that are together and putting their magnetism against the protons to keep them there makes these elements that are like, you know, up in the upper above the hundreds, because most of the elements that are super heavy are actually from like, you know, 60 to 90. Okay, like you know, bismuth, what is atomic number of bismuth? Like 83. Okay, so from 83 to like 100, like they're so unstable, it's crazy. But like this new electron shell or whatever makes them, even though they're so heavy, they have 117 protons alone in the middle group. Probably, you know, 12, probably like 100 and some protons as well. Protons and neutrons. I mean, neutrons are neutrally charged things that a lot of atoms have that makes their atomic weight and their atomic number different. But also electrons don't weigh anything. But so basically, what it is because of the counteracting magnetism from the new shell, these elements above the hundreds are able to exist for a lot longer than they should without like they have the same number of protons. They keep their number of protons, 117 protons in this case, will stay together, you know, for a significant amount of time, as opposed to like a couple attoseconds, which is the shortest amount of time in the universe or whatever. It says here that it lasted tens of hundreds of milliseconds, which is, you know, for stuff that's after bismuth, like in the 90s, like in the atomic number 90s and stuff, that never happens almost, or something like that, you know, like, or at least by our calculations, something that's this heavy should only last for a couple milliseconds at best before it sheds protons and neutrons and electrons and shit and doesn't become, it's not actually tennessine anymore, you know. So what happened was, you know, because of that, they can exist for so much longer than we thought, and we can synthesize them and prove that they exist based on how long they existed and how long whatever it was that they decayed into existed. Like, you know, atomic number 115, because it lost 2 protons when it decayed, and then it did it again and again and again. That's usually how it happens. They actually don't exist for very long. What happens is they emit radiation until they reach something that is stable for a couple hours. And they're like, okay, it decayed this many times, and this is its atomic number for 6 hours. So it, doing the math backwards, it must have been tennessine. And it's like, wow, that's, humans are crazy. We created an element for, you know, not even 1 second or a couple seconds, and we just were like, okay, it's real, you know. But that is so cool to me that we can actually synthesize elements. In fact, this graph helps. Okay, so this is the reverse math thing I just said. They made the tennessine here, and then it decayed some neutrons or something because its weight is lower, and then it decayed into 294 is the atomic weight. So then it lost, and this lasted for, you know, 45 milliseconds, a second, you know, whatever, and then 7.5 minutes, and then 33 hours for whatever this green one is. And then the same for this way, they did it 2 different methods. That only lasts 38 seconds? Anyway, but this lasts for 33 hours, and then they can, check the energy that it lost and all this shit. And be like, okay, it must have actually existed for a certain amount of time, and we can prove that based on some kind of calculations that I don't understand or know. And this is the island of stability thing. So the darker the color, the longer it can survive without, the longer it keeps the same number of protons, 117 in this case. And it, you know, that amount of time that you can live, doesn't exist in this state. It doesn't exist over here. It doesn't exist right here. But all this stuff is uh, you know, this is like bismuth is down here and stuff. And then radioactive elements, and then nothing. When you get into this lighter green, it decays after a second or less. And then there's this, a year or a little more than a year block that doesn't seem to follow the rest of the graph. You know what I mean? Like this should be this color too, based on what it looks like is going on, but it's not. It's like, what? And they realized that it's like, it says here that in the 1960s they thought that, the closed shells from 114 to 184 could counteract it. Blah blah. It's crazy. So I can't explain it, anywhere close to how good this page explains it. But also, it's because I'm trying to do it in layman's terms, kind of. Anyway, I've been reading up on this, and it's really cool. That's why it's in this video. I love the idea of this, and I have just got back into reading about it. Like the other day. Anyway, that's gonna wrap it up for today's check-in or whatever. Thank you so much for sitting through that. If you did, I sincerely appreciate anyone listening to me ramble, you know, nonsensically for that amount of time. If you want to subscribe or leave a like, that would be so great. If you want to comment, likes and comments help a lot with like recommendations and helping my channel grow. I don't care if you ring the bell. It doesn't matter to me. I don't have the bells on because I don't want notifications from anything but like texts and stuff. And I'll put this link in the description after I remember, and you guys should read up on it. It's really cool. If you know enough about this to understand this page. If you want to learn more about it and get to where you can understand it, there's people that can explain things better than me are on YouTube, like Veritasium, Vsauce, Smarter Everyday. Maybe Smarter Everyday probably doesn't know this much about chemistry. Not that he's not super smart, but there's chemistry channels and stuff where you can kind of get introduced to this enough to kind of get the gist, and actually get the gist from reading this, you know, essay. This is like a fucking like scientist essay, official chemist, essay. Thank you for watching, and remember that I believe in you, and having confidence in yourself is good. And whatever you may think that you're ashamed of or you're doing wrong, unless it's hurting somebody else. If you think you're lazy or something, don't worry about it. Just let it go. You're doing the best you can. I know that you're doing the best you can. You need to know it too. And also, we can create new elements, you know, only because we know that we can, or that we know that we see, we probably shouldn't even be doing this. We did it because we could. And they tried to do this for like 10 years. If they tried that hard for 10 years and they did this, you know, don't give yourself crap for taking a month to do something, because you know if you can do the same thing that anyone else can do. So after 10 years, if they discovered a new element, what could you do in 1 year? I don't know, what your dreams are, but you can make progress. And just however long it takes you to make progress doesn't, determine your worth or your drive or your ethic or how good of a person you are or if you matter. You obviously matter. Maybe it's not obvious, but you do matter. What you're going to do with your life matters. I'm not good at motivating, but and you're going to do great things, and if you don't do them right now or within the next whatever years, that's fine. Some people go to college at age 12 and some people, don't do anything until they're 50. And all of those people are still great. So just remember that. I'll see you later.